Hey kiddo, welcome back. As you can tell by the title of the video, I want us to expand your knowledge, your tools, and your skill set when it comes to doing mathematical proofs that involve integers, with a focus today on even and odd types of questions you would get. We're going to be expanding on what even and odd means definition-wise, what type of examples you would see, and the steps you need to take in order to solve them. So sit back, relax, and let's get you ready for that test. First thing we need to do is we need to do a recap of all of the knowledge you need to know for the video today. We're going to do a few kind of shorthands. So we're going to do something called there exists. It is a backwards E, and it just means it's a short form to say the words there exists. Another shorthand we use is an upside down A to mean for all. And we're also going to do a shorthand S dot T for such that. Those are all the short terms we need to know. So let's begin with the definitions of even and odd. So the definition of an even number is as follows. Definition. An integer n is even if there exists an integer k such that n is equal to 2 times k. The best example for this kind is if you get a question that basically says prove the integer 4 is even. How you will go about this is basically say, okay, from the definition, I know I need to find another number, k, such that our integer here, 4, is 2 times that. So let's just take 4 and say that this is 2 times 2. Therefore, there exists an integer k, we will say here k is equal to 2, such that 4 is equal to 2 times k. Therefore, 4 is an even number. Again, proving that 4 is even is a very straightforward example, but it gives us an early look into into how we're going to handle the future questions today. Okay, now that we've done even, let's now do odd. So we say, the definition is going to be very similar. We say an integer n is now odd if there exists another integer k such that n is equal to 2k plus 1. An example we can do with this one is example prove what's a good word for this? Prove 9 is a odd number. In order to show that, we will do the same before. 9 is equal to 2 times 4 plus 1. Therefore, there exists an integer k equals 4 such that 9 is equal to 2k plus 1. Therefore, 9 is odd. Again, something I want you to focus on when we're doing these definitions is that we're always coming back to doing this. And that is the same for every type of proof. You always want to go back to what in math the definition of it was, because that's how you are going to relate the math equation to the actual statement of even and odd. With that out of the way, let's begin with some examples. Today, all of our examples are going to be using a particular proof method. This is called the forward-backward method. This is basically a technique where this is the most straightforward technique that we end up using for proofs. The idea is that you start with all of your assumptions. I will call these A. You will then state using all of the definitions that exist in there, all of the numbers, say A equals K equals something or N equals something. You will then work backwards, starting with the answer B, where this will basically state, okay, in math notation, if you're trying to prove it's even, we need something of this form. And then finally, the middle part is where you spend a majority of the time on an assignment or on a quiz to basically fill in the two in-betweens. But doing these steps first, then coming into the math one, it is a lot easier for you to see what step ends up coming next. Okay, example. The sum of two even integers is also even. So this makes sense when we go through some examples. So we say 2 plus 4 is 6, which is even. 4 plus 10 is 14, which is even. 20 plus 2000 is 2020, which is also even. So we see from from just looking at some initial examples of this that this is going to probably be true. So let's try to see if we can prove it using the forward and backward method. So first, we need to start with listing all of our assumptions that we'll call the A section for this. So the assumption here is that we start off with two even integers. So let's write it. Let's say let A and B be even integers. And now if we flip over to the bottom, we will now state what we want the other one to, when we need the answer to be. So the answer to this is that the sum of these two is even. So we need to show A plus B is even. Okay, so let's use the definitions of even to see what our next steps would be. So according to the definition of something being even, it means there exists another integer such that each of these numbers is equal to 2 times that number. So let's say this means there exists a C and D. There exists integers C and D such that A is equal to 2 times C and B is equal to 2 times D. Okay, next is we get to work with the in-between of everything. How do we get this one to then show that A and B is even? Well, again, according to the definition, we need to show that A plus B is equal to 2 times something else. What this something else is, we are not sure yet. So let's start with the steps with A and B and work our way down. So A plus B is equal to 2C plus 2 times D. Again, remember, we need to get it into this form. I see a 2 in both of these terms, So let's try combining them. If I factor these, I will then get c plus d here, and oh, that's starting to look like the right form. So a plus b is equal to 2 times two other integers that are guaranteed to exist because a and b are even. So technically, this step right here did this one. So now we just need to add one more additional step. We will say, therefore, there exists an integer k equals c plus d such that a plus b is equal to 2 times k. Therefore, a plus b is even. So let's summarize what we did. We took our original question with the forwards and backwards method. We wrote down all of the things we were assuming for it, and we wrote down the thing we need to prove, the final statement. We then worked forwards from the top using the definitions of even to state math-wise what a and b had to be. We then worked backwards using the definition of even to say what a plus b needs to be. And then we started working with the in-between here, where we noticed maybe we need to get a plus b. We started by adding a plus b together using the top statement, grouping the twos together, and that led us to show that c plus d was in fact the k we were looking for. Let's do another. So let's say, let n be an even integer. Then n squared is also even. Okay, let's start with our forwards and backwards method. We're going to state what we're assuming. We're assuming that n is even, and our final statement is going to be n squared is even. Okay, let's look forwards and backwards again with this. We know that n is even, therefore there exists an integer k such that n is equal to 2 times k. And here we need to show that n squared is equal to 2 times something else. Okay, so we have n here. We need something in terms of n squared. Let's start with the math stuff in the middle. So we'll take n squared and apply our first one to get 2k squared. Breaking this out of the bracket, we will then get 4k squared. Again, when doing the forwards and backwards method, we know what kind of form we need this to look like. So it's a lot easier to then say, okay, let me factor out a 2 from this, and I'll get 2, and then in brackets 2k squared. So we say, therefore, there exists an integer. We need to give this another letter because we've already used k, so maybe we'll say c is equal to 2k squared, such that n squared is equal to 2 times c. And therefore, n squared is even. So again, we're going through these questions because we're really trying to hammer in those steps that are used in the forwards and backwards method. Take your question, write down all the assumptions, write down the conclusion, use the definitions that you know of to then write down something in math terms for each of the assumptions you have. Do the same with the conclusion, and then we can start kind of working with the steps we need to go from here to our final one here. So let's do another example with that one, where now instead we are going to work with odd numbers. So let n be an odd integer. Then n squared is odd. let's work through our steps again. Our assumptions, n is odd, and our final statement b is that n squared is odd. Okay, this is our first time working through an odd example, so let's showcase what happens with the definition. Similar to even, this means that there exists a k, an integer k, such that n is equal to 2k plus 1. Okay, this is where the forwards and backwards methods become really important, because now if n squared is odd, we need something of the form n squared equals 2 times something else plus 1. This is going to be a little bit trickier than doing something with even that just involved factoring out a 2. But now that we know what kind of form we're looking for, we can do this. All right, so we have n as a formula, and we need n squared. So let's start with all of the math stuff in between, and let's do n squared. So we know that n is equal to 2k plus 1 squared. If we expand this out using FOIL, we will get 4k squared plus 4k plus 1. Squared 2k double plus 1, perfect. Now remember, we need to get this form here. So we have the plus 1 at the end, which is perfect. Now we need this to somehow be 2 times something else. If we factor out a 2 of both of these, we will get 2k squared plus 2k in the brackets times 2 plus 1. Therefore, there exists an integer c such that c, which is equal to 2k squared plus 2k, such that n squared is equal to 2 times c plus 1. Therefore, n squared is odd. Example, let a be an even number and b be an odd number. Part A for this question is going to be show that a plus b is odd. B is going to be a times b is even. And those are the two we're going to try to show. So let's start with A. So for both of these, it's going to be the same, but we're going to start with our assumptions. We will have A is even and B is odd. Our conclusion is going to change slightly for part A or part B, so let's do the first one first. We will now have A plus B is odd. So working forwards, we need to state that this means there exists a C and there exists integers C, D such that A is equal to 2 times C and B is equal to 2 times D. And finally, we need, since A plus B is odd, we need A plus B in some form of 2 times something else plus 1. Let's work through the math in the middle. Okay, so we have A plus B is equal to, this should be plus 1, since that is odd. Perfect. Subbing these in, I have 2 plus C plus 2 D plus 1. We will just ignore the brackets for now. Now we need to look at what we have that's similar and what we have that's different. So we've got our plus 1 at the end. That's great. Now we need to factor out a 2 from these ones. So we will get 2 times C plus D plus 1. And with one final statement, we will be done. Therefore, there exists an integer, we will call this k, which equals c plus d, such that a plus b is equal to 2 times k plus 1. With that, part A is done. Now we can do part B. So again, the first part of this is going to be the exact same. Our assumptions are the same as in part A. Now the only thing that's going to change is that A times B is even. And working backwards, we need to show AB is equal to 2 times something else. Okay, so let's start with the math in between. AB is equal to 2 times C times 2D plus 1. And we can technically factor this out to be 4CD plus 2 times C. This part gets really confusing for a lot. That's why having this here shows us what form we need this to look in. If I need a 2 out of this, I will factor out a 2 to get 2CD plus C. And now I have found my form in the middle. Therefore, there exists an integer k, which is equal to 2CD plus C, such that A times B is equal to 2 times k. Therefore, A times B is even. So let's summarize what we did today. Our goal was to kind of start introducing proof techniques and steps you need to do in order to handle even and odd questions that you would have on your assignments, on your exams, on your quizzes, etc. We went over the forward and backward method, which is the standard when it comes to doing these type of proofs, and when doing even and odd questions, how we use the definition, forward and backwards, with the math stuff in between to end up with our proof for these. Thank you very much for watching today. I hope this was very helpful for you, and if it was helpful, let me know in the comments. And feel free to put another trickier question down below that I can respond to. I would love to see the type of questions you're getting as practice for your tests, your assignments, etc. for your classes. Anyways, I've been Mac. It has been a pleasure to have you here today, and good luck to you, kiddo. You got this.